All right, if you've ever coded anything with AI, you definitely know the feeling. You hit run, you're feeling good, and then bam! You're staring at an error message that might as well be written in another language. But what if I told you those errors aren't just frustrating roadblocks? They're actually puzzles. So today we're going to put on our detective hats and learn how to crack the code.
Yep, there it is. That giant, intimidating wall of red text. We've all been there, right? This whole thing is called a Python traceback, and let's be honest, it really feels like your code is just yelling at you. This specific one, an OSError, is probably super familiar if you've spent any time with the Hugging Face hub. It looks like a total dead end, but trust me, this is where our detective story actually begins.
So, let's totally reframe how we look at this. That error, it's not a failure. It's the first set of clues on a treasure map. We just have to learn how to read the map.
So, let's kick off our first case. It starts with a super common story, right? A colleague pings you a model ID they've been working on, you're excited, you want to check it out, so you plug it into your code, hit run, and it just breaks. Instantly. And that, my friends, is where our investigation begins.
Okay, so our main piece of evidence in any of these cases is going to be the traceback. And I know, it looks like a whole lot of technical noise, but there's a secret to decoding it, and you'll be surprised at how simple it actually is.
Now, this is going to feel wrong. It goes against every instinct you have, but this is the golden rule of debugging. You have to read tracebacks from the bottom to the top. Seriously, the real story, the actual problem, the most important clue, it's always right there at the very end. If you can just master this one thing, you're honestly halfway to solving most of these cases.
All right, so let's put our golden rule into practice. We look at the very bottom line, and what do we see? An OSError. And it even gives us our first lead. It's telling us to check the model ID. So that's step one. We're going to take that ID and pop it right into the search bar on the Hugging Face hub.
And boom, there it is, our first big break in the case. The search on the hub gives us nothing, which is weird, right? But if you look really, really close, you spot the tiniest clue, a typo. Dilbert should only have one L, not two. See? Sometimes the most gigantic problems are caused by the absolute smallest mistakes. So, okay, let's fix that and try this again.
But of course, it's never that easy, is it? We fixed the typo in the model ID, but now we're hit with a brand new error. This time, though, the traceback is being super specific. It's telling us the model repository is missing a file, config.json. The plot definitely thickens.
So, our new lead says there's a missing file. But how can we be sure without having to leave our code and go digging around on the web? Well, it's time to bring in a special tool from our detective kit. There's a handy little function in the Hugging Face hub library called list repo files. It lets us peek right inside that model repository. It's basically like getting a search warrant for our investigation.
So we run that function, and what do we get back? A list of all the files. And yep, the results are crystal clear. We see the model weights, the tokenizer files, but just like the traceback told us, there is no config.json. It's gone. It looks like our colleague just forgot to upload it. Simple as that. Okay, so now the solution is actually pretty clear. The model's name itself gives us another huge clue. It was fine-tuned from Dilbert base uncased. That means we can probably just borrow the config file from the original base model. So we'll use a tool called autoconfig to grab that default configuration. Then we use another function, push to hub, to upload that missing file right back where it belongs. It's kind of like performing a little bit of digital surgery.
And now, for the moment of truth, we try loading the model one last time, and it works just like that. Case closed.
All right, let's tackle our next case. This one's a little bit trickier because we're going a level deeper. We've actually loaded the model successfully this time. The problem happens when we try to use it, when we actually pass data through it, which is something we call the forward pass. So this isn't about missing files anymore. This is about the data we're feeding the model.
Okay, here's our new clue, an attribute error. And the message is actually pretty helpful and direct, if you know how to read it. It's saying that something in the code is trying to call a .size method on a plain old Python list. But here's the thing, Python lists don't have a .size method. So right away, that tells us there's a fundamental mismatch happening somewhere deep inside the model. And this right here, this is the absolute heart of the problem. You see, big models like transformers, they don't operate on standard Python lists. They need a special kind of data structure called a tensor. Tensors are built for the super high-performance math these models have to do, especially on a GPU. So our tokenizer gave us a simple list, but the model was expecting a heavy-duty tensor.
Here's a good way to think about it. A Python list is kind of like a general-purpose shopping bag. A tensor, on the other hand, is like a specialized reinforced toolbox. You just can't use a shopping bag to do a toolbox's job, right? And that's exactly what our code was trying to do. The model needed to use a tool from the toolbox, that .size attribute, and the shopping bag just didn't have it.
And what's great is that the fix for this is just beautifully simple. All we have to do is go back to our tokenizer, the thing that prepares our data, and just tell it what we need right from the start. We add one little argument, return tensors equals PT. That's it. We're just telling it, hey, give me PyTorch tensors, not Python lists.
And with that one tiny change, we run it again, and the model works perfectly. Boom, another case solved.
So, we've cracked two very different cases now. But what's really cool is that in the process, we've actually been assembling a powerful, universal debugging toolkit that you can use for pretty much any bug you run into. So what exactly is in our detective's toolkit? Let's recap. First, and most importantly, read tracebacks from the bottom up. That's our golden rule. It'll always point you to the real culprit. Second, just Google the error message. I promise you are almost never the first person to see a particular bug. Third, always verify your inputs. Check for typos in your model IDs, check your data types, all that good stuff. Fourth, use the tools the hub gives you to inspect the repository files directly, so you're not just guessing. And finally, when you're really stuck, don't be a hero. Ask the community for help.
See, with these principles in your back pocket, you're not just a coder anymore. You're a detective. You now have a repeatable method for turning those cryptic, frustrating errors into clear, solvable puzzles. So, what's next? The very next time you see that wall of red text pop up on your screen, don't get discouraged. I want you to see it as an invitation. It's a brand new case that's just landed on your desk. All the clues are there, just waiting for you to piece them together. So the question is no longer if you can solve it. The real question is, how quickly are you going to crack the case?